Now, in 2 dimensions, you either have lines that intersect, or they don't intersect, or they're exactly the same line over and over again. And if they don't intersect, they're parallel. Now, in 3 dimensions, we're going to be able to have 2 lines that aren't parallel, but still don't intersect. Right? Like this. So if you want to find out if 2 lines are parallel, all we're going to have to do is look at their direction vectors. But you can also set up your system of equations to solve it, and you're going to have all your variables disappear and get a false statement, like 0 is equal to 5, or 3 is equal to 7, something that isn't true. Then you're going to know that that system is not going to be able to solve, and you'll know that those 2 lines are parallel. So here's an example. Okay? Maybe you can see from the direction vectors already that these are parallel, but we don't know for sure that they're not on the same line. Because if they're parallel, they could still be exactly the same line. So if we were going to solve this with matrix equations, we could look at our parametric forms. We know that our x value from the first one is 1 plus 3t, and our x value from our second equation is 2 plus 6s. Our y values will be 2 plus 2t, and our y values from our second one is 3 plus 4s. So what that creates is 1 plus 3t has to equal 2 plus 6s, and in our second set of equations, 2 plus 2t equals 3 plus 4s. Now you can choose however you want to solve this, because now we've created those black equations. We've got 2 equations with 2 unknowns. You can use old techniques of substitution and elimination. You can use new techniques of matrices. You can choose whatever you would like to solve for this. You want to do matrices? So if you wanted to do matrices, your first equation here, if we rearrange this, I'm going to have 6s minus 3t equals negative 1. So I just brought my variables to one side. And on my second one, I'm going to have 4s minus 2t equals negative 1. If we wanted to set up a matrix equation for this, 6, negative 3, 4, negative 2, st, negative 1, negative 1. And then you would have to figure out your inverse. So discriminant of our first one is going to be 12 minus a negative 12, which is 0. Okay. Oops. See the problem we're having right now? 1 over 0. And if we could keep going, we would switch those and make these negative, negative 1, negative 1. Right? This is not possible. We have no inverse available. This is not solvable. And so when we run into a problem like this with matrices, then we know that these two do not intersect and there's no solution. If we had gone about this and tried to use substitution or elimination, personally I like elimination here. You pick a variable that you'd like to eliminate. Say you want to get rid of the t's. I'm going to multiply this equation by 2 and this equation by negative 3. Because then I'm going to get 12s minus 6t equals negative 2. And over here I'm going to get negative 12s plus 6t equals positive 3. When we add our equations together, all of our variables cancel out, and we get 0 is equal to -1. Yeah, +1. All right. Good. Perfect. Which doesn't work. And so there too is telling you that there's a problem. No solution exists, so they must be parallel. You can also have them intersect at a single point. Another word for this is concurrent lines. So in this case, when you do go to solve for it, you will get values for s and t, and those values will work out to find that intersection point. Same thing as before, you would set up your parametric equations. -3 plus t for our first equation, and our second equation is going to be 4 plus 3s. And our y coordinate is 5 plus 2t, 3 minus 2s. And from this, we'll get two equations with two unknowns. -3 plus t equals 4 plus 3s, and 5 plus 2t equals 3 minus 2s. Again, you could rearrange this and use matrices. You could isolate. In this case, it looks like it's be really easy to isolate t and use substitution. Or you could use elimination. I would take this first equation and multiply everything by -2. -6 minus 2t equals -8 plus 6s. And then we still have 5 plus 2t equals 3 minus 2s. Adding those equations together, -1 plus 0 equals -5 plus 4s. Add 5 to both sides, 4 equals 4s. So s is equal to 1. And once you have s equal to 1, you can plug that in to either equation and find out what t is. So 5 plus 2t equals 3 minus 2 times 1. 2t equals -4. T is equal to -2. So what happens is you're able to find a value for s and t. You're able to solve for it. And then if we want to find the actual point where it intersects, we can plug in either -2 for the t or 1 for the s. Notice that when you do that, here we're going to get 7 and 1. And here we're going to get something else. Okay, so where did I make my mistake? When I multiply by -2, oh, I didn't make this a -6, right? So then that will make this, yes, that'll make a difference. When you add, you got -8s, then you'll get, is that right? -6x, -8s. All right. Oh, and my other, look at this. I'm doing really well. There's another mistake. Wow. Is it Monday? It is, right. Yeah, it is Monday. Okay. Well. Make that into 11. Works out perfectly. Everything else then is good. Once you move the 5 over, you get 16 equals -8s. And you get s is equal to -2. We have to go back and change this. So the nice thing about this system is when you put it back in and you check both of your equations, and you're supposed to get a point of intersection, and the point comes out differently, as we see here, it tells you you made a mistake somewhere. And then you just have to go back and find out where that mistake is. Fortunately, we made multiple mistakes. So 5 plus 2t equals 7. So t is equal to 1 and s is negative 2. Kind of crazy that that was. Now t is equal to 1 and s is negative 2. So now when we check it out, we're going to get negative 2, 7, and negative 2, 7. Yes! Much better.
So when they say show that, what do we have to actually write on it?
So you're going to have to, when you're asked to show that they're concurrent, you're going to have to solve for s and t, and then you're going to show that there is an intersection point. Okay? And technically it would be enough to show that there is a solution for s and t, because that then implies that there is a solution. But I would go so far as to actually, as this example shows, to find out what that point is, because if you made a mistake earlier, that's where it's going to show up. So now that we know that negative 2 comma 7 is the intersection point, we know that they're concurrent lines because they do intersect. And then you've got coincident lines, lines that line up exactly the same, which means there's going to be an infinite number of solutions. So we're going to set up our system of equations, and then your variables are all going to disappear, and you'll get a statement that's always true. Whereas before, with our parallel lines, our variables disappeared and we got a statement that never was true. Now you're going to get a statement like 15 is equal to 15, 7 is equal to 7. That's always true. We're going to look at what happens with matrices as well here. See if something interesting happens when we try to solve it with matrices. Same thing, we'll set up our parametric equations, x and y. So 1 plus 3t equals 7 plus 6s, and 2 plus 2t equals 6 plus 4s. So if you would multiply the first sets of equations by negative 2, and our second set of equations by 3, then you're going to get negative 2 minus 6t equals negative 14 minus 12s, and 6 plus 6t equals 18 plus 12s. And when we add these together, 4 plus 0 equals 4 plus 0. We get 4 is equal to 4, which is always true, even for big values of 4. Now I'm curious what's going to happen here. If we had set this up, 3t minus 6s equals 6, and 2t minus 4s equals 4, what would happen if we had set this up as a matrix equation? So we would have had 3, negative 6, 2, negative 4, t and s, 6 and 4. We get that determinant of 0 again, eh? Do you see that? Negative 12 minus a negative 12. So in that first example, when we got that determinant of 0, we said, oh, it doesn't work, and then we applied that there must be parallel, which is true, but we weren't able to tell from that if they were parallel and never intersecting or parallel and always intersecting. So in this case, I don't think you could show that anymore with matrices, because matrices would, in this case, not allow you to go further than this. Because as soon as you try to do an inverse, if you set this up as an augmented matrix and you tried to change it to reduced row echelon form, what would happen? I think there'd be all zeros in the bottom. Can you see that if you took row 2 and did negative 2 row 1s plus 3 row 2s, this wouldn't change. This will be 0. This will be 0. And then this will be 0. So in this case, what you've done is you've reduced it from 2 equations with 2 unknowns, and basically reduced it to 1 equation with 2 unknowns. And 1 equation with 2 things that are still unknown has an infinite amount of solutions. It's a line. And a line has all those points that make it true. So it's another way of showing that there could be an infinite amount of solutions. So those are all ones that we've seen before in 2 dimensions. Now in 3 dimensions, you can get 2 lines that aren't parallel, but still don't intersect. And those are called skew lines. And there's an example. 2 aircraft flying at different altitudes. They're not necessarily flying parallel to each other, but the cloud lines that they leave is a good example where they wouldn't intersect. At least that's the plan. You try not to make planes intersect while flying. And sometimes planes can intersect lines as long as they don't do it at the same time, right? That's not a bad thing. But it's even better if they don't even intersect their pathways even at a different time. So what will happen in a case like this is you might be able to solve for S and T, but then it won't work for your third equation. Because when you set up your system of equations, because you'll have 3 parametric equations, one for x, one for y, and one for z, you can still solve a system of 2 equations and 2 unknowns and find out what S and T are, but when you plug those values into equation 3, it doesn't work. And then you would know that you would have skew lines.